the design process and the manufacturing process in a very abstract way are completely linked. Like they're inseparable. This is kind of like a very organic, abstract, kind of almost art approach to this, which can then change the way we think about how we design an injection molded part, perhaps.
Hello and welcome to the Being an Engineer podcast. Today, our guest is Duann Scott, a driving force in the world of computational design and additive manufacturing. He's the founder of CDFAM, a global symposium series connecting engineers, designers, and developers, pushing the boundaries of digital fabrication. From his early days at Shapeways to leadership roles at Autodesk and nTopology, Duann has helped shape how we design and make things. He's now leading the charge at the 3MF Consortium, bringing structure to the digital thread for additive manufacturing. Duann, thank you so much for joining us today.
Thank you for the opportunity. I appreciate it.
Well, let's talk about CDFAM first. Tell us, what does that stand for, and what's the story behind this? How did you create this?
CDFAM could stand for anything, really, but it starting as computational design for additive manufacturing. And it was kind of as a joke because like DFAM is kind of hard enough for most people. So adding a computational element to it is like another step of complexity. But I think it's what's critical to realize the potential for additive manufacturing. So if we just go towards additive manufacturing design with our existing framework of how we design and engineer things, we're not really typically going to get the performance and productivity gains that you need to justify the cost of 3D printing things, which is typically more expensive than other ways. And so it started off as a bit of a joke. And then the URL was $1. So when I was thinking of starting a design conference for 3D printing, it was cheap and it had easy SEO because no one else was using it. So I called it CDFAM. And then as the event has evolved, it's grown to cover computational design at all scales, not just additive manufacturing. And that happened very, very quickly. Like within the first year, I was scaling up to architectural applications of computational design processes because there was such a pull from that industry and others. And so now CDFAM could mean computational design for artificial intelligence and machine learning, if that's what you want it to be.
Got it. Talk to us a little bit about computational design. I mean, how do you define that? How should we be thinking about computational design? What are some examples?
I'm sure there's some academic examples and some arguments that are going on, ranging in especially architectural academia, about what computational design really is. But for me, it's really about building the systems, including algorithms, to meet multi-objective requirements for a part's performance and manufacturing or construction process simultaneously, and being able to weigh those different requirements against each other to produce not a single optimal design, because optimal is like a razor's edge, which if you move across in any dimension, it breaks. But a robust design, which meets all of those requirements that you've then sort of fed into it via data to sort of build a system to make the objects. So you're not really just designing a single object or a single mechanism or a single part or a single building, but a system to solve the design decisions and then make things, whether it be one-off or a series of things in the world of mass customization.
Would general CAD programs qualify then as computational design? I mean, effectively, it's a huge algorithm, right, with a lot of custom inputs that output a design.
Typical CAD systems are kind of linear in their programmatic way. You may be able to drive an Excel spreadsheet to do a design of experiments to sort of explore the solution space. But unless it's bringing in other data about, say, simulation data of performance or the manufacturing process or its ecological footprint. You're kind of not bringing all the data together in one platform to solve that design problem. There are slowly there's starting to be ways that you can sort of drive data into the design process. But your typical sketch, extrude, loft, radius on corner isn't really computational design. It may be parametric, but it's not really bringing in data to drive things. It's sort of a linear process, which has solved many, many, many engineering problems and will continue to do so. But some of the more gnarly ones, it's just not enough data to drive decisions to do as well as we can.
Yeah, that's a good distinction. What are some examples of true computational design?
We can look at it from scales. So let's start small. So if you're designing a medical implant, let's say a bone graft for a cancer patient, you're taking in scan data as a DICOM, you're dissecting it, you're programmatically analyzing the density of the bone to know where to cut. You're programmatically putting in angles of where you're going to make those cuts, and then you're automatically making a jig so the surgeon can use that to cut the bone. And then you're generating the geometry which is going to replace it, which you're using a ladder structure to increase in osseointegration and allowing for the load that's on the bone structure. It's going to happen as the person, assimilates that titanium into their body without, causing more problems. So you've got these multiple objectives you're sort of dealing with simultaneously, and you want to do it programmatically and repeatable so that you're not sort of manually doing this every time you need to do an implant. The surgeon doesn't have these skills, and the typical, biomechanical engineer, they're expensive. So you want to sort of take their understanding of process and embed it into a system which is then reusable and applicable through different, for different similar but different applications.
Yeah. Are there any pieces of software out there that you can recommend, or maybe not even recommend, maybe you don't want to put your stamp of approval on it, but share that engineers, designers listening to this might be interested in checking out?
The backbone of computational design has been for the past 10, 15 years, has been Grasshopper within the Rhino platform. By whatever quirk of the history of how CAD systems are developed and how this particular software came to be, it's a very open system, which is affordable at a student level and has been taught in architecture for over 10 years. And so there's thousands and thousands of people who have learned, particularly in architecture, how to programmatically design systems to make things. So because of that, we see a lot of the footwear companies, the major sportswear footwear companies that you all know, love, and wear, hire architects as part of their computational design team to build these systems. And if you think of how, because they know these computational workflows from doing, building facades 10 years ago, and from facades to footwear, you think it's not that big a jump, no pun intended, because you're really just building a system which you're then applying through different sort of requirements.
How have you seen computational design evolve over the years? Kind of where did it start, and what are the capabilities these days?
There's some academics who'll tell you where it started. I don't really know. Where it's evolving is from large scale down. So from, as I said, from architectural facades, sort of like took the first edge because you could do these cool designs, and people like Zaha did these undulating forms which are algorithm driven. And then as the platforms matured, they started to use it for things like figuring out the HVAC system in buildings, and then, calculating sunlight reflections, so that you don't make some sort of Archimedes death ray into a car park of a skyscraper and, burn people's buildings, burn people's cars as has happened in the past. So you're using these calculational systems to predict performance of a building over time. And that sort of led the wave. And then as it came down to smaller scale, then, the medical device sort of, like bone integration, osseointegration sort of came from the small up. And we're sort of slowly meeting between these two chasms are coming together as we see different applications which have similar multi-objective problems. And that's, now it's moving its way up through the high performance, automotive, aerospace, and then it'll go, and then into, sports equipment. And then it'll slowly make its way into more like consumer facing objects. But for now, it's high performance, similar to what we've seen in the engineering space, in additive manufacturing, where it has to be like something has to pay its way. So to set up these systems, it takes time. Like if you're going to design a simple bracket, you don't need to computationally design that setup because you can, calculate the load and figure it out pretty quickly. To pay for that time of basically someone who's half designer, half software engineer to produce that workflow is an investment that you need to, amortize. And so the product has to be of enough value or being used enough times to make that worthwhile.
Does all computational design require some software skills, or are there programs out there who have dumbed it down for those of us who aren't skilled in writing software?
Yeah. So there are companies who sort of help people build workflows which can then be reused by those who don't understand what's going on behind the scenes. Things like Shapediver basically allows you to build a workflow in Grasshopper and then, make a UX for it in a browser, so people can then use that to modify a given geometry type to meet their requirements. So there are ways to access this without doing all the work yourself. And we also see in architecture and mechanical engineering is that a larger firm will have a computational designer on staff who will then build modules which other designers and engineers can then use, and they share that internally. We also see that at nTopology, where I worked for a period. You could also build these custom workflows which you could then share internally or externally. And then that would sort of give you a jump up, so you could then just bring in your requirements or some other data to then drive the geometry or simulation, and then run with that without knowing how to do everything from scratch, because there is a learning curve.
Okay. You've been involved a lot with standardization of file formats within the additive manufacturing space. You're laughing. Tell me why. What's going on?
From motors and robotics to controls, automation, and precision prototyping, Simutech brings ANSYS simulation tools and expert insight directly to your team. We help you accelerate design, reduce risk, and eliminate costly rework.
Validate before you fabricate. Simutech Group helps you simulate thermal stress, vibration, fluid flow, electronics cooling, electromagnetic performance, you name it.
Whether you're in automotive, aerospace, energy, industrial automation, or the next big thing, Simutech partners with innovators to deliver simulation-driven results that move products forward. Build smarter machines, launch stronger products, scale faster with Simutech's simulation support by your side.
Simutech Group, your engineering partner in motion. Visit simutechgroup.com and let's power up your next design.
It's a file format. It's young men don't dream of creating a file format. I don't think. Well, I didn't. Sure.
But no one thinks about this, right? But it actually is really important to the field.
Yeah, it's critical. It's painfully critical. So in my roles at both Autodesk and Shapeways to a certain degree, but nTopology, I was working on partnerships between software and hardware companies. And each time we tried to do an integration, it took months of just making sure the plumbing would work. And we could get data from the software to the machine and validate that everything worked. And it was the duplication of effort and the small quirks of just decisions that were made 20 years ago, which in additive manufacturing is a long time ago, which still affect us today in a negative way, just needed to be overcome. So when I left nTop a couple of years ago, I was already sort of involved on the periphery of the 3MF consortium, and I sort of stepped in to help sort of with awareness adoption and to sort of get things to the next level on the political level. Like, I'm not doing anything technical. I'm not doing any coding. I'm not telling people how to structure these things because that's not my area. And so I just helped to sort of connect things and get more growth of the adoption of the format. And now we also are now an ISO standard as of early this year. So now technically, you can rely. We've been working on this for 10 years. So it's got 10 years of testing, of validation by a third-party QA company. So we're not like, and the consortium is from every major CAD company, software company, and hardware company, who are usually bitter rivals. So you don't usually get Dassault, Siemens, at Autodesk sitting at a table trying to solve problems together. They're more likely to try and make things hard to switch between platforms. And this is a rare occasion where the technical people got to get together and without any sales or senior management people sort of blocking any sort of communication. And we have a data format which works to communicate more than just geometry in a very efficient manner.
You mentioned this is a rare situation. Why do you think it is that technical professionals from these different entities, different companies agreed to get together and collaborate on this?
Microsoft produced FOMO. So when there was the hype of 3D printing taking over the world, Microsoft looked at how that's going to be adopted and saw the STL format and the other formats that were under development sort of in the space and said, this will not do, this will not work. We need a robust format which is human readable and extensible so we can do everything that's required for additive manufacturing to sort of bring it into mainstream. And once they sort of said they were working on this, then Microsoft as an operating system, every CAD platform runs on Microsoft pretty much, unless you're doing a server based on Linux. But, every engineer's got a PC, not a Mac, because this is where the software is. So once they said we're working on this, all the CAD packages said, okay, we'll do what we can to make sure that our systems work with this data format that you're proposing and investing in developing.
So tell us a little bit about the 3MF file format and how that has facilitated standardization across additive manufacturing.
Yeah. Okay. So the core of a 3MF file format is a mesh format, similar to what an STL is, except it's always watertight. It has no, you're not going to have an issue with the mesh not being solid, so you can always print it. It has units. So you know what size it is. So an STL format it's not a millimeter or an inch or a foot or a furlong or a yard. It's just some triangles. And it's more efficient because the vertices are counted once instead of 3 times as the STL is. So the base is just a way more efficient way of communicating the surface of an object. But then we have extensions for the production process, for materials, for slicing, for beam lattices, for ladder structures, for implicits, for volume stacks, as in a bitmap stack for volumetric 3D printing. So there's just way more data that you can encapsulate and communicate in the file format without increasing the size much, depending on the flavor you're using. So companies as diverse as HP and Bamboo Labs use 3MF as a container for their entire build information, not just the geometry, but all the parts within it, all the material specifications, all the machine specifications, and then any other metadata around the user's information. If it's a service bureau, is all embedded in this one format. So it's very robust and powerful.
I just purchased a Bamboo Lab machine and I'm very happy with it. It was
cool.
Interesting to hear you talking about that. So STL, you mentioned, right? I mean, that's ubiquitous. STL is like, it's everywhere. It seems like in the world of 3D printing, additive manufacturing. Are there indications that 3MF is at some point going to overtake STL file formats?
I don't know. Human nature is deeply flawed, so we never know what people are going to do. But I think as the younger generation who are growing up with a Bamboo Lab default to 3MF now because that's what they are growing up with it from school.
Yeah,
and it's just the file is a third the size. So I know we have infinite hard drive space in theory, but we don't. And if you're sending stuff to a service bureau to get printed or stored or shared, if you're sending it as an STL file, it's 3 times the size. You're kind of doing a disservice to everybody involved to have such a bloated format when it's just a basic thing, So I think that as the kids come up and they'll default to 3MF, it'll slowly become this archaic thing, and someone out there will try and defend it as STL as being superior because that's what they grew up with, but there's no real reason to be using it anymore unless the software is also archaic and doesn't support 3MF.
Yeah. Okay. All right. Going back to computational design for a moment here, and thinking about traditional manufacturing processes like injection molding, casting, things like that. Are there a lot of use cases?
Yeah,
because
absolutely.
A lot of people listening to this podcast, they're using these very traditional manufacturing processes, injection molding and CNC and casting and whatnot. What are the use cases for those kinds of processes with computational design? The Product Development Expo, or PDX, is your chance to learn from subject matter experts providing practical, hands-on training for dozens of different engineering topics. GD&T, Advanced Surface Modeling, DFM, plating and finishing techniques, programming robots, adhesive dispensing, prototyping tips and tricks, and lots more. PDX happens October 21st and 22nd in Phoenix, Arizona. Learn more at pdexpo.engineer. That's pdexpo.engineer.
So the ideal situation is you increase the performance of the part you've designed using this process, and you optimize for the manufacturing process simultaneously. So you could have rules in the design process about wall thicknesses, and like if you're doing injection molded parts, you can optimize both the design of the part and the design of the mold simultaneously. And so if you change sort of one requirement, like a material change or a ejector pin change, the design can modify with it automatically. And you could do a trade-off. You could do like simulation of using machine learning would be the ideal way to do it. But you could do a simulation of sort of 100 different variations upon the same design and find the one which has the best trade-off between manufacturing time, cost, and performance simultaneously. So we're seeing that we had a company called Framus who kind of manufacture a lot of again, going to footwear, major footwear companies, shoes in Asia. They're using computational design to both guide the design of the shoes themselves, the performance, as well as the molds. So sort of using simulation and lattice structures for conformal cooling of the mold to sort of decrease the cycle time. So it's not 3D printing is sort of leading the way in some areas because it's such a gnarly problem and such an expensive process that to make it worthwhile, you need to sort of optimize for the design, and not everyone knows how to do that yet. So this is a way to sort of speed up that process. But we're seeing companies just like this, so using this for sheet bending and machining and milling. So it's not just additive for sure.
You mentioned the phrase design for performance. What's the difference between design for performance and design for, insert your favorite traditional manufacturing process?
Oh, this performance of the part after you've manufactured it. So you're optimizing for how it performs in the world, whether it's, a mechanical response, whether it's a like ensuring that it has the right sort of ecological footprint. So the performance can be, any objective you have for the lifetime of the product in use is how I use that term. And then process, I think of as a manufacturing process, including any sort of post-production inspection.
Yeah. Okay. Well, I'm going to take a short break here, share with everyone that the Being an Engineer podcast is brought to you by Pipeline Design and Engineering, where we don't design pipelines, but we do help companies develop advanced manufacturing processes, automated machines, and custom fixtures, complemented with product design and R&D services. Learn more at teampipeline.us. The podcast is also sponsored by The Wave, an online platform of free tools, education, and community for engineers. Learn more at thewave.engineer. And we are privileged to be speaking with Duann Scott today. So Duann, let's talk a little bit about AI, which everyone is talking about, but how is AI starting to influence computational design, and where do you think it's going in the next few years?
I think it's the other way around. I think of computational design as building the data platform for AI and machine learning. So AI and machine learning is only as good as the data you're feeding into it. If you feed it images of rabbits and like game geometry, or poorly constructed CAD that's in a database from people who have abandoned their files because they don't care about them, the results you'll get from training your AI, your text to CAD system, will be that garbage. So you're not going to get anything good out of unstructured public data from what I've seen so far. When you're building a computational design workflow, or even just like you have the mindset of how you're building a computational design workflow, you're bringing data together about the performance of a part, the materials, the manufacturing process, costs, like recycling, like all this other information about what your design intent is and what your manufacturing intent is. And then you're using that to make a decision. So once you have all that data sort of that you're using to analyze, you can then use that to train machine learning to then accelerate decision making next time for something that's similar, not for a generalized. You can't use the data you've used to design the bracket for an air conditioner to then design your jet engine. That is not how things work. So if you're working in a particular field and you've got similar problems, then the data you gather during the design process, if done well, can then be used in the future to accelerate the design process, the engineering process, not to replace it. You're basically cutting down the cycle time for simulation or for problem solving or for getting opinions from people, because you sort of have those opinions baked into your algorithms, which are then used to, you can then use AI/machine learning to give you a down selection of results within the Pareto curve of results you've done previously. So you can't use it to design something outside of your known, but you can use it to find a valid solution which meets your requirements inside of it.
Let's go back to CDFAM for just a moment here. I'm curious to hear a little more about how you started this, because it's grown over the years. And I think, hopefully I'm not misremembering this, but I think you remember telling me that it's now in the US and European countries. Is that accurate?
Yeah. I currently run it twice a year, once in New York and then once in a European city. So it was in Amsterdam what day is it? Just a month ago now. And then last year it was in New York and Berlin. And next year it's going to be in Barcelona, New York, and Tokyo. So I'm going to run one in Asia as well, because people are having trouble traveling that far to go to events in Europe or US. Yeah. So it started because it was the event I wanted to go to. That's pretty much it. Yeah. So I've been, in the design and 3D printing space for a fair amount of time. And the events that I went to were very machine, material, and process focused. There wasn't a lot about design and software. And so I would present at every conference typically, and I would be there on Thursday afternoon when everyone else is at the airport talking my talk. And then, there'd be a few excited people, and then everyone else had left. So I just wanted to bring people together who are excited about design as I am, so we can sort of share ideas and learn from each other in a very non-salesy, pitchy way, but a very just pure knowledge sharing and networking. Yeah.
This is very interesting to me because I am in the middle of developing PDX, the Product Development Expo, which is happening for the first, technically for the second time, but in the first real way this October 21st and 22nd out here in Phoenix.
Cool.
And I had the same idea as you, which is this is the event that I would like to go to.
Yeah.
This is the event that I think would be fun, and it doesn't exist, so let's build it.
Yeah.
It's been a ton of work, and I've learned a lot, but very satisfying work. I imagine your experience has been similar. I'm curious, what were a few of the biggest challenges that you had to overcome in the beginning?
The beginning was not knowing whether there was enough people who would be willing to commit their time to come and present, and then whether there's enough people to come and who'd fill a room to make it worthwhile for those people to present to. And I've been in the space for a while, and so I've had a decent network of people I could call on and ask if they're interested. And so I got a good program to start off with some really exciting speakers, and it was, it was everything that I hoped it would be, in that it was informative and informal and fun and inspiring, and, both down to very technical things at material level up to conceptual. Like there were people who were using AI and machine learning to develop and analyze and sort of rank material performance down at the literally molecular level. And then there was also someone who was working for Yeezy using large-scale robots to 3D print mycelium for shoes in a very experimental way. And
mycelium for shoes. I hear about mycelium for mushrooms. I don't think I've ever heard it in the context of shoes.
So this researcher, she was from Australia. She moved to LA to work with Yeezy, now Additive, and she had done a PhD by training a robot to be responsive to the growth of mycelium and feed it to make it grow in a given form. And then,
oh my gosh, that's crazy.
Yeah, it was wild stuff. And that led her to be poached by Adidas to think about how they could rethink, footwear and packaging using, natural processes. So emergent forms. So these are on the same stage. So that's what I was looking for. It's like this broad ideas shared, and then how people make the connections between them is what's interesting.
That's wild. I'm no expert, but my understanding of mycelium is it's the kind of thread-like interwoven lattice structure underneath the ground that eventually forms the fruit mushroom that we see above ground.
Yeah.
So you're saying training a robot to feed that mycelium in a way that it grows into a very specific intentional shape, like a shoe sole or something like that.
Yeah, she was doing it into an emergent shape. So it was like an interaction. So this robot took 2 months to grow this mycelium. So it was slowly feeding it, had a sensor, and seeing when an area was dry, it would drop some nutrients and water in that area so it would continue to grow. It wasn't making it a performant footwear at that stage, but the concept of how we can evolve forms, and sort of what's interesting is sort of the design process and the manufacturing process in a very abstract way are completely linked, they're inseparable. So if we think about the design and manufacturing process as this inseparable flow of data going through it, this is kind of like a very organic, abstract, kind of almost art approach to this, which can then change the way we think about how we design an injection molded part, perhaps.
That's fascinating. I had never heard about that. Okay. Where can people go and learn more about CDFAM?
CDFAM.com. As I said, the URL was $1. It's easy to get to. CDFAM.com. The next event will be in October 29th to 30th. So just before Halloween in New York. Halloween in New York is always fun. We've got an amazing lineup again. of people from, like researchers from MIT using AI and machine learning to develop materials again, because I think this is really important. Up into a number of footwear people from New Balance and Puma. And then because we've got to have footwear, we have got to have architecture. So we have people using machine learning, and sort of other interfaces for understanding the data that's driving decision making in the built environment. So we've got a lot of interesting. There's more and more machine learning coming into the event as the field evolves and things become more real.
That's terrific. Was there ever a moment over the past, several years as your symposium has grown that, you overheard a conversation, or maybe a friend forwarded you something and you realized, wow, the CDFAM community is really having an impact in the industry. This is exactly what I hoped would happen.
It's only been going since 2023. So I'm only a couple of years in now. But I constantly hear of partnerships and adoption of new technology because they found out about it at CDFAM, which is like the ideal situation. It's about bringing people together. And I won't say this is entirely true, but the outcomes, like the physical outcomes of what are made with it, aren't as interesting to me as the way we approach things and how we work together. And so that's what I'm really encouraging, because, I can't be an expert in every application of everything that uses every software. Like that's not gonna, I can learn a lot in the process of building these events. But what I sort of can find is how to get people to work together from broad fields to solve when they have an abstracted version of similar problems. And when I see, someone from the medical device space being called in to work with someone in the aerospace industry for a given, like a filter they're thinking of. Like, so if someone did a presentation on how osseointegration may happen, and then they're using that same idea for filtering chemicals to help with a chemical reaction, that's cool. That's what's interesting, like when it's abstracted out.
Yeah. Yeah. Do you have any pro tips for how you have seen or facilitated disparate groups working together, right? You might mention like medical devices and different industries, and seeing them all come together at CDFAM and work together and collaborate. Any pro tips for others of us out there who might be trying to bring dissimilar industries together to collaborate as well?
I think looking for the similar problems, which is in my world, it's like multi-objective, multi-stakeholder problems, whether a stakeholder might be a surgeon, a manufacturing engineer, and the client who's getting an implant, or a developer, a council, an architect, and a client for architecture is sort of like these multiple problems. Everyone's got very strong opinions about what they need, and often they compete against each other. So finding, gnarly problems like that is where I'm finding a sweet spot in finding people who then have the same sort of multi-objective problems at different scales, or a different output, or a different input.
Yeah, terrific. All right. Well, Duann, where can people get in touch with you?
I think there's a contact form on cdfam.com. That's probably the best way to go.
Okay.
And I'm on LinkedIn as well. If
Perfect.
Connect personally with me, and I usually answer messages.
All right. Well, Duann, thanks so much for your time today. Is there anything else that you want to bring up about CDFAM or cool file formats, or anything else that you think would be useful or listening to the listeners out there that we haven't touched on yet?
If you're transferring or storing data for 3D printing for any application, you're kind of doing a disservice for yourself if you're not using 3MF. It's free, it's open source, and it's extensible. So no matter how complex your problem is and how niche, you can use it to solve the problem for you and your customers, your clients, or whatever. If you need help applying it, you can ping me and I can get someone who's technical to help you apply it. if you want to
Awesome.
learn about more design approaches to design, check out CDFAM. All of the recordings from the presentations that are legally possible are free online on YouTube and as a podcast, not as a like questions and answers like you and I are doing, but just as a recording. So all that information is free where possible. And have fun. There's exciting new tools and exciting approaches to design which are opening up, and it changes the way we can solve problems.
Fantastic. Duann, thank you so much for creating CDFAM and building that community, and also for sharing some of your precious time with us today on the podcast.
Thank you. It's been fun.
I'm Aaron Moncur, founder of Pipeline Design and Engineering. If you liked what you heard today, please share the episode. To learn how your team can leverage our team's expertise developing advanced manufacturing processes, automated machines, and custom fixtures, complemented with product design and R&D services, visit us at teampipeline.us. To join a vibrant community of engineers online, visit thewave.engineer. Thank you for listening.